All right, so let's go ahead, create a part, 2D, deformable shell, approximate size 200. No, we're working in the smaller units, so let's give a value of 10. We're gonna go ahead and draw a couple of circles with the dimensions of let's make that 1.75 for the radius. And then the other one, draw another circle from that same center with a radius of 1. And then I'm going to do my usual thing, meaning drawing a line going from the center horizontally to intersect the outer circle, and then draw another line from the center vertically to intersect the outer circle. And then we're going to delete a whole bunch of things by using this icon, which is auto trim icon, trimming all of these things except the quarter circle, like that. That's what you should end up with. All the units are in inches, so it's steel. Modulus is going to be 2991130. Its Poisson's ratio is equal to 0.3 is what I used for simplicity. We'll go to plasticity. We are going to simply pick the first one, which is the plastic information. You'll notice what happens on the information that you're asked to provide. The first information must correspond to the value that you have. So here I have the yield stress is equal to 59,822. And can you tell me what should the plastic strain be for the first data? It has to be 0 because that is the yield strength of the material that I'm inputting as the first input value. Then I'm going to continue that, enter, and the next point is going to be 64,450. Tab gives me the next plastic strain, which is 0.000, 841. Next one would be 68,500. And the plastic strain is going to be 0.0029. 269, make it. And next one is 72,000. And the plastic strain is 0.00753. Finally, 75,000. 0.0173. So these are some stress strain data that I've tabulated. Of course, when you have a stress strain data, you don't want to give 1,000 data points in here. You want to break it into critical locations and give it a few data points like what you have here. Okay. In case you want to take a look at this thing, let me go to plastic and just highlight these things. And I'm going to right click on it and say create XY data. Do you see that in the bottom? Okay, so it's going to read X values from column 2. That makes sense. I want strain to be in the X axis, so I'm going to call that a stress strain. Let's say OK. Again, right click, highlight all your data points, right click, and then do create XY data. So you've created an XY data, and you should be able to plot that data if you want. As a matter of fact, if you go under visualization, there is this XY data that we haven't talked about. That's create XY data. There's also XY data manager. That's the one you want right now because you've already created one. XY data. And all you need to do is simply say what? Plot. And a miracle occurs. This is the stress strain data that you're providing to the program in this case. I knew he would ask the question. Go ahead.
So are we going to make these come up with that plastic deformation number ourselves, or is it something that you give to us?
Yes. Okay, so we're going to dismiss, and of course that's going to remain until you switch the module to your part or properties or wherever you are. Sections. Remember what I said we were going to do? What kind of problem are we solving? It's a plane strain problem. This is section of a tube, long one. We're going to give it plane strain thickness of 1. And then we'll say, okay, assign the section. Pick the whole thing. I'm going to undo create set and say done. Plane strain. And then create an instance of the assembly, just like you've done before. Nothing unusual here. Okay. Have you kept up with me? Those of you who are working on your computer. Now comes the fun part. Steps. So here I want to do what? Do I want to do linear elastic first? Yes. So I want to do static general. So I'm going to call that linear elastic solution. Don't touch this thing. We will touch that later. And load. What do I want to do for the linear elastic load? Okay, it's a pressure load that I'm applying here. And interior, say done. Magnitude is 30,000. Say okay. Now, this is a quarter of a tube that I've cut. What boundary condition do I need to apply? Symmetry boundary conditions on 2 planes. So this is going to be X symmetry. I don't use this first item. I use displacement rotation instead. I'm going to go ahead and pick the lower segment horizontal line and say done. What do I need to restrain? U2. And next boundary condition would be Y symmetry. Pick the vertical line on the left-hand side and restrain U1. Okay. We're going to switch to the mesh assembly. What element do I want? Plane strain, right? Is that correct? Notice it defaults to plane stress. We're going to go with plane strain. I don't want reduced integration. Question for you. What else do I need to do, if anything? Do I want incompatible mode, or do I not care about incompatible mode, or does it make a difference? I'm just going to keep the regular default formulation. And I'm going to keep in mind that eventually I'm going to do plasticity analysis, so I want to have a reasonably fine mesh. All right? I am not going to do convergence study. I'm going to let you do that on your own. However, I do want to create a structural mesh Assign mesh control. Don't say quad dominated, quad. Structured. Okay. Let's see what happens if I say the default of 0.25, 2 coarse, 0.1, better, meshed apart, and I have 176 elements. I'm going to refine that further by noting from my own intuition that as I'm applying the load, where is it going to possibly do plastic deformation first? Inside, outside, inside. Okay, so I'm going to do a couple of edge seeding in this case. I'm going to pick these two edges. Did I pick that one? And I'm going to do seeding by number. It picks the default value that you had. It's equal to 8. I'm going to make it equal to 15. And bias that, single biasing, ratio of 2. By the way, in case you're wondering what the double biasing is, it starts small from both ends and kind of goes large toward the center, or starts small in the center, flares out larger toward the two end. And we'll say apply and see what happens. Seems reasonable to me, does it? No, one of them is reverse. So select flipping. Should I flip this one? Is that better? I'm going to mesh the part and see what it looks like now. Does that sound good to you? All right. So I'm anticipating, in this case, ahead of time. This is going to be a linear static solution, obviously. So we've created the mesh. We're going to create a job. Okay. Save my and submit this linear static job. Notice I've actually applied the correct load. So from the results of the von Mises stress, I should be able to make a determination whether the yielding will take place or not, as he suggested. We're going to look at the results and deformed shape, superimpose the undeformed shape as you were expecting. This is going to be the outcome. And what do I have for my von Mises stress maximum? 63,360, perfectly uniform. Can you tell me whether this mesh is reasonable or not? It better be. Okay. So do you remember the stress strain data that I had provided? Is it going to yield? Okay. So it is going to yield. Everybody agrees on that one. Okay, so you've done your linear static analysis. Everything is okay. I'm going to go ahead and collapse that model. Copy that model to now plastic model. And open up the plastic model. I've defined everything so far as materials, except that in the steps, I'm going to simply, you have one of two options. Place it. I'm still going to stay with static general. Continue. This flag, you don't touch that for the time being. Can you tell me what that stands for? Nonlinear geometry flag. That's NLGEOM. For now, we're going to stay as it is and go to the incrementation tab. You notice what happens? Maximum number of increments is equal to 100. Can you tell me what that means? It's going to take the load, maximum load, divided into 100 increments of load. Increment size. Notice what the initial value for default is? 1. What does that mean? The first increment is going to be the maximum load. You don't want that, right? So you have to give it something a little bit smaller. Maybe 0.25. That means I'm going to guess as the initial increment, quarter of the load. Minimum, you notice what it is? 1 times 10 to the minus 5. Don't touch that one, ever. Maximum, 1 is okay. Now, what happens in the program? It takes your initial increment, goes through the number of iterations of the Newton-Raphson approach. What is it? We have no control over it. Abaqus decides that automatically. Solves the problem. Can it converge to the solution in that first increment of load based on the number of iterations? If it exhausts the number of iterations, cannot approach it, do you think what's going to happen next? No. My initial increment that I said is 0.25. Notice there's the minimum associated with that too. Since my initial increment did not converge to a solution, it automatically divides that by 2. And so my next load increment then is going to be, instead of 0.25, it's going to be 0.125. If it still doesn't converge after the required number of iterations, it's going to divide that by 2. It's going to repeat this process until it hits the minimum value. If it hits the minimum value and still cannot converge, it'll kick out the solution and say, you got problems. Very rarely that would occur. Okay? That's the sequence of steps. The thing that you don't have any control over is the number of iterations of the Newton-Raphson approach. That is done internally automatically by the software. Some other programs, such as Nastran, allow you to control that as well. Let's say it reaches the solution with 2 or 3 increments. Say, oh, maybe my initial increment size was too small. So the next increment multiplies that increment by 2. Starts with an increment of 0.5. After 2 or 3 iterations, it's reached a solution. Say, oh, I can even increase that more. You know what I'm saying? But the maximum is 1. Sometimes you may want to be careful with that maximum of 1. Reduce that to 0.5 even, meaning don't go beyond half of the total load being your increment. Maximum number of increments. Notice maximum number of increments. It repeats this halving or doubling process. If the maximum number of increments exceeds, you're in trouble again. You can change that, of course. So I'm going to rename this thing, since this is not linear elastic, this is plastic. Now comes the field output. Going to double click on field output 1. Notice the frequency of the reporting of the results is every n increment, n being 1. Maybe that's not a good idea because increments can be uneven. Instead, you can say, how about every x unit of time? Remember, this is not really time. Horizontal axis was what? The division of the load. So the load was like this, and then it came down like that. I'm using the x-axis to divide the number of load. So I'm going to say, I'm going to go from 0 to 2, the maximum time. I want to obtain, let's say, 20 data points, 0.1 unit of time. Or you can leave it as default, n equal 1. History output, that's okay. I won't touch it for the time being. I'm going to define an amplitude, however. We're going to do the tabular I'm going to call that load unload. Notice the other ways that you can define things. Continue. Time is 0. Amplitude is 0. Time is 1. Amplitude is 1. Time is 2. Can you tell me what the amplitude is going to be? 0. You can plot that if you want to. Hopefully you don't have to. Notice the time span is a step time. There's also this concept called smoothing. Sometimes it starts with a kind of a 0 slope in the beginning, although you define a ramp, but it goes a tiny slope in the beginning, the fillet radius, if you will. Same thing in the top. That's the smoothing. That happens a lot in the impact analysis. We'll say, okay. And now what I want to do is go back, modify my load, double click on the load. Instead of amplitude being ramp, I'm going to give it my load unload as the corresponding amplitude. Yes?
Before you said we choose a load of 1. Do we do that?
You can either do it here or in the amplitude. So in this case, I define amplitude being 1.
Okay.
The load gets multiplied by that. I'm still retaining my original load. You can define amplitude being equal to 30,000, but then you have to come back here and change the load to what? 1. The boundary conditions are okay. We're not going to touch anything. The element formulation is not going to change. So nothing to do here. Just go ahead and create a solution set. Let's submit this thing and monitor the job. Pay close attention to the monitoring. Warning. That warning is irrelevant, pretty much, but you notice now I'm having multiple stuff going on here. Step 1, how many increments did it take to solve? 1 increment, how many iterations? 1. With 1 iteration at each one of these initial 8 increments, we were able to achieve the convergence, because that was a pretty regular problem. The 9th and 10th iteration required 2 iterations. There's a good chance this is where things went beyond the yield point. But you have a solution, theoretically. Right-click, look at the results. And von Mises stress is not going to give you a whole lot. You notice the increment is 10, step time is 10. Instead, I'm going to click on the first increment, which is the double-headed arrow pointing to the left. And instead of S, I'm going to look at quantity that is known, PEEQ. Equivalent plastic strain is what it is called. First increment, no plastic strain. I'm going to step through. Second increment, nothing. Third, 4th, 5th, 6th, 7th, 8th increment. Do you see what happened? In the 8th increment, 9th increment, plastic strain is going further in. 10th increment is where your plastic strain has finally finalized. And what is the magnitude of the plastic strain is given by these values. Think of it as a von Mises equivalent to plastic strain, meaning all the components of the plastic strain, not along radial or tangential or x and y directions, everything combined.